Is cheap filament really bad? Or is expensive filament unnecessary? Today we're looking for the answer to this. There are hardly any people with a 3D printer who haven't asked themselves this question. You use a filament and you're satisfied with it. Then an ad pops up in front of you. Or maybe you see a different filament in a video, I don't know. Or a friend says, hey look, there's this new filament, it gives great results and it's pretty cheap too. Cheap. Now when I print with my filament, it costs this much. If I print with that one, it'll be much cheaper. Within a year, I could even make back the cost of the machine. Now we're confused. Let's not kid ourselves. Especially if a spouse, a friend, or someone we know recommends it, we want to try it out. We're going to talk about all this in detail, but now something just came to my mind. Here's a question for you right away. Test yourself. Let me line up the prints I've made side by side like this. Just by looking at them, try to guess which one was printed with budget filament, which with mid-range, which with expensive, and which with very expensive filament. Pause the video right now and write your answer in the comments. Then after the video ends, we'll talk about it again. Let's see how accurate your guesses will be. Of course, it's perfectly natural to think of it this way. You might be using a budget filament. You encounter a problem. You immediately blame the filament for the issue. You say, let me buy a slightly more expensive filament, maybe my problems will be solved. Or the exact opposite situation could also be the case. You might be using an affordable filament. You are completely satisfied with everything about it. But then you wonder, if I buy a slightly higher quality one, could I get even better results than I do now? Of course, there are dozens of brands and hundreds of types of filament on the market. Therefore, it's almost impossible to make definitive statements about this. But I thought that if a test was conducted using generally preferred and well-known brands, it could give us an idea. I immediately did my research and bought PLA filaments from 4 different brands, each in a different price segment, which I predicted would be preferred by users. One of these is cheap, one is mid-range, one is expensive, and the other is very expensive filament. I can't mention the brands of these because they are not brands that wanted to be featured in this video of their own accord. I mean, to be honest, I didn't even make them an offer. Also, the tests I conducted could be binding or misleading. So I don't want them to come to me tomorrow or the next day saying, can take down this video or something like that. That's why, when considering these, we'll only be talking about their prices. As for Creality, since it is featured in this test of its own accord, there is no problem in mentioning the filaments in its own price segment. Of course, this also brought a nice advantage. On one side, we have 4 different filaments that will compare solely based on their prices without specifying the brands. On the other side, there are 4 different filaments from the same brand, but in different price categories. We will also be comparing these with each other. Let me specify their prices as follows. To keep the information up to date, I won't mention a specific price. But as you move from the cheapest to the most expensive, the price increases by about 1.5 to 1.7 times with each class you move up. To illustrate with a simple visual, for the same amount of money, you can buy one of the most expensive filaments, 1.5 of the expensive filament, 2.85 of the mid-priced filament, and exactly 4 of the cheap filament. There were certain points I paid attention to when comparing the filaments. One of these is whether the companies are manufacturers themselves. You don't see any contract manufactured brands here, because with contract manufacturing, one day they might have company A produce it and the next day company B. This can disrupt quality standards. However, all the brands you see here are manufacturers themselves. I also made sure that the material was not PLA+, because PLA+ filaments can contain different additives. This can also alter the structure of PLA. I used a single printer for all the tests. As you can see, it's the Ender 3 version 4 model from Creality. I was also planning to shoot a review video for this printer, so it turned out to be a great testing process for me. Because I almost used up all the filaments, to be able to do this test, I needed to trust the printer. To be honest, it didn't let me down. Bed leveling, flow calibration, and so on all work flawlessly. It's a very rigid printer. Whenever I finished testing one filament and moved on to the next, I changed the nozzle. I used a standard 0.4 mm nozzle because if the nozzle gets clogged, I wanted to better understand whether it was caused by the filament. Of course, perhaps most importantly, I printed everything using the same settings. With the standard settings in Creality Print, I used a speed range of 200 to 300 millimeters per second, the nozzle at 220 degrees, the bed at 60 degrees, and the environmental conditions were exactly the same. So what will you find in the video? First, we will look at the surface quality. Did I encounter any issues or problems during printing? Was there any stringing? Did it sag at sharp angles? How was the bed adhesion? On the technical side, how consistent are the filaments' diameter and ovality? In addition, with the tensile break test, you will also be able to access technical information about the material's resistance to tensile force and its flexibility. At each stage, I will score each filament individually, and in the end, we will all see together which filament received the highest score. Let's see if the scores given at the end will match the predictions you made at the beginning. So, let's get started. Although it's not a very important criterion for me, I know that some users pay attention to this. That's why I wanted to check the winding quality of the filaments. As you can see here, the windings of both the very expensive and the cheap filaments are quite neat, while the expensive and mid-priced filament looks a bit tangled. Interestingly, the situation was not much different on the Creality side either. While the Creality Hyper PLA and Ender PLA had a neat winding, the CR and Ender Speed PLA looked a bit tangled. Now let's move on to the test prints. The first print, of course, is Benchy, the indispensable model of our tests. When I look at the print I got with the very expensive filament, I can say that it is a completely flawless print. I don't see any issues or problems either in the surface quality or in the areas where there might be even a slight chance of sagging. The flat top surfaces are quite smooth. I didn't set these settings myself. The print was made using the ready-made G-code setting included in the Ender 3 version 4. When I switch to the expensive print, the surface on the bottom looks matte and nice. However, when I get to the upper parts, there are some shiny spots in certain areas. This is caused by the device slowing down at certain points. This is related to these settings. However, in the standard Creality print settings, it needs to slow down at certain points to improve cooling. Other than the color change in these areas, I didn't encounter any serious problems. On the flat upper surfaces, there were small gaps. When I look at the filament in the mid-price segment, the print quality is still quite successful. Although there is no problem with the surface quality, there are minor droops in places like doors and windows. There is no color change at points where it speeds up or slows down. There are also no gaps on the top surfaces. It came out quite smooth. In the print made with cheap filament, the bottom surface still looks matte and nice. There's no problem with the surface quality, but the color transitions are very sharp. In other words, there are areas that go from very matte to very glossy. When I look at the top surface, although there are no gaps, the nozzle marks are quite noticeable. I will do my scoring out of 4. Since there are no defects on it, I give the very expensive filament 4 points. My score for the medium filament is 3, because there is no color change at all. Although there are some minor droops, I didn't encounter any other problems. The expensive filament gets 2 points. There are significant transitions from matte to glossy on it, and there are also small gaps on the flat surfaces. As for the cheap filament, it gets 1 point. Even though the outer surface quality isn't bad, I think the transitions from matte to glossy are too frequent and sharp. Let's continue with the same prints on the Creality side. I don't notice any problems in the print I made with the Creality Hyper. There are very minor droops around the door areas. Other than that, the surface quality is quite successful. There isn't any transition between glossy and matte on the general surface of the model. The top surfaces have come out quite smooth. You can see the print I made with Creality CR PLA. Again, there is no problem on the outer surface. There are very minor droops in the window sections. There is no change in the surface gloss. It can be said that the result is quite close to Hyper PLA. Here you see the print made with Ender Fast, the PLA filament from the Ender series designed for fast printing, just like Hyper. The surface quality is again successful. The surfaces transitioning from matte to glossy are very subtle. I don't know if I'll be able to show this to you in the photos. Even the eye has a hard time perceiving it. There is a slight roughness on the top surfaces. This print was made with Ender, Creality's most economical series. As with all of them, the surface quality here is also quite successful. While there is no sagging in details like doors and windows, the matte effect is more pronounced on the lower parts. However, in areas where the speed drops, shiny surfaces have formed again, and on the top surfaces there are some gaps that can be considered extremely minimal. If I were to rank my scores for Creality, in my opinion, the best print was achieved with Hyper. After that, CR Filament comes in, albeit by a very small margin. My score for CR PLA is 3. There were changes in glossiness with fast. That's why I give it a 2. With Ender, however, this was more pronounced. So my score is 1. Right after this first print, I want to briefly step in for a moment. We'll continue quickly. I'm saying this to inform those without experience and to provide an explanation for experienced users. The color changes you see from matte to glossy are related to the settings. In general, when 3D printers print faster, the material starts to become matte. When it prints more slowly, these kinds of glossy spots appear. You can completely eliminate this with the settings. So making an object entirely glossy or more matte is actually up to you. However, as I mentioned earlier, in standard settings the printer automatically slows down at some protruding areas or small points to make cooling easier and reduce sagging. This applies to the standard settings. If you turn it off, sagging may increase a little. Maybe the print quality might decrease slightly, but this color difference will disappear. What I actually wanted to see here was whether the filaments would show this color change even at different speed settings. That's why in all the prints I took, I used this setting I mentioned both to get better results and to observe this difference in gloss. I wanted to mention this so you keep it in mind when evaluating the prints from now on. The next model is this spatula, which I printed using a ready-made G-code file included in the Ender 3 version 4. In the print I made with the very expensive filament, I didn't notice any printing issues. Since the top finishes in a circular shape and the layer height wasn't set very fine, you can see the layer lines. This is perfectly normal. When we switch to the expensive filament, the surface is still matte, but there is a certain shine on the lower parts, that is, where the overhangs are. There are also small imperfections where the spatula curves inward. Again, I noticed some small gaps on the very top surfaces. Now let's look at the mid-priced filament. There is still a bit of shine in the areas with overhangs. It's not as much as with the expensive filament, but it's there. The front side is completely smooth. There are also no gaps on the top surfaces. The model has come out quite nicely. When I look at the cheap filament, all the surfaces appear matte. The transition between matte and shiny is very minimal. Most of it is matte, but especially on the front surfaces there is a significant roughness. There are no gaps on the top surface, but the overall surface quality is not very good. Taking into account the print quality here, I think it's very expensive, so it gets 4 points. The mid-price segment gets 3 points, the expensive filament gets 2, and the cheap filament gets only 1 point due to its poor print quality. Let's see what kind of result was achieved on the Creality side. The hyper is quite nice. Although it's not very obvious, there is a transition from matte to shiny. The angled part at the front has come out very smooth. There are also no gaps on the top surfaces. The print quality is successful. I'm moving on to the CR filament. As with the Benchy, a result very close to the hyper has been achieved again. The transition from shiny to matte might be a bit more pronounced than it is on the hyper. There's no problem on the front part that angles inward. There are also no gaps on the top side. Now we're looking at the print I made with the Creality Ender Fast filament. The surface is generally matte. Shininess has again appeared on the angled parts on the sides. There are a few rough spots on the part that angles inward. Again, there are some rough spots on the flat areas on top of the model. Although the print made with the Creality Ender is similar to this, I can say that the results are a bit better. Overall, it has a matte surface. There are some minor rough spots on the front, though not as much as with the Ender Fast. Similarly, these rough spots continue on the top surface as well. But as I said, the Ender has produced a slightly better result than the Ender Fast. As a result of these outcomes, Hyper receives 4 points in the scores I gave to Creality. CR again, just barely behind. Maybe both could have been given 4 points, but according to this system, one of them had to get 3 points. That's why I'm giving CR 3 points. The results of the Ender and Ender Fast were also close to each other, but I think the surface roughness was greater with the Fast. Therefore, while the Ender gets 2 points, the Ender Fast PLA receives 1 point. Again, I wanted to add a brief explanation here. Some of the things you see here are, of course, also related to the printer itself. For example, the surface roughness that occurs. Here, both the printer and the filament have an effect. Or for example, soon we'll look at stringing and angle tests. Here, the printer's impact on the print is significant as well. That is, you might use the same material on a different printer. Stringing might occur there, but not on this printer, or there might be more sagging on one than the other. You might be able to print with the same filament on a different printer without any sagging at all. The important thing here was just to know this. The same printer was used. The nozzle was changed each time as well. So if there was any mark, sagging or stringing somewhere, the conditions were completely equal. Otherwise, we certainly can't say that all the results here are entirely related to the filament. Now, let's continue from where we left off. This piece you see here was also something I made for the Ender 3 version 4. Of course, I have a lot of these now. You attach this to the side and it collects the excess waste produced during especially colored prints into this box. Since it has curves and a lot of flat surfaces, I thought it could give us more insight about the quality of the filament. What you see here is a print made with a very expensive filament. Although there is a slight gloss on the outward angled parts due to the lack of slowing down, this has not affected the overall surface quality, and especially the flat surfaces have come out extremely smooth. When we look at the inside, there was a surface here that covered the vast majority of the print bed. An almost flawless, perfectly smooth surface with virtually no roughness or gaps has been achieved. Now let's move on to the expensive filament. Once again, in areas with right-angled protrusions, the transition from matte to glossy is quite sharp. This sharpness here has also affected the overall surface quality. In fact, I can even see some minor roughness in certain spots. There are both roughness and glossiness issues present on the model. When I look at the flat surface on the inside, I notice some small gaps and roughness in certain areas. Now let's look at the print made with the mid-range filament. Again, in areas where there are right angles, the transitions between matte and glossy are quite pronounced. It's not as sharp as with the expensive filament, but it's still quite noticeable. Here too, the color transition has affected the outer surface to some extent, but the surfaces are completely smooth. Again, when I look at the flat top surface, there is nothing I can point out as a problem. Now, let's look at the print made with the budget filament. At the point where there is a right angle, the transition between matte and glossy is again quite sharp. The overall surface is extremely matte. In fact, this matte finish nicely hides the layer lines, but in my opinion, the material is not very suitable for high-speed printing. That's why there are quite significant rough patches on the surface. Overall, I can't say the surface quality is successful. When I look at the flat surface inside the box, similar gaps and roughness continue. As a result, the very expensive filament gets 4 points from me again. The mid-range filament also maintains its consistency. It gets 3 points. While the expensive filament gets 2 points, the budget filament continues its negative consistency and gets 1 point. You can see the print I made with Creality Hyper PLA. As you can see here, there was a gloss transition in all the filaments. This continues with the Hyper as well. However, this gloss here hasn't affected the overall surface quality. It has a very smooth surface. When I look at the inside, I can say that this is perhaps the best result I've seen so far. Just like with the expensive and mid-range filaments, a smooth flat surface has appeared here as well. The print I made with the CR filament also shows similar results. In general, CR has always produced results very close to Hyper anyway. There is a gloss in the area with the right angle. I can say that it has had a slight effect on the overall surface quality. The marks are a bit more noticeable than with Hyper, but the layers are not distinct. The outer surface is smooth. When I look at the inside, maybe it's a notch behind Hyper, but I still see a smooth top surface. We continue with Ender Fast. Just like with all the others, the gloss continues in the area where it angles outward. Here too, the outer surface is quite close to CR and Hyper. The layers are indistinct and the surface quality is quite successful. When we look at the flat surface on the inside, although there are no gaps anywhere, I will try to show you up close. In some spots there are these dotted rough patches. If the same thing had happened on the outer surface, I would say it's pretty bad, but since it's on the inner surface, maybe it can be overlooked in a print. Still, the result is not better than Hyper or CR. You can see the print I made with Creality Ender PLA here. Here, the transition between glossy and matte is not as obvious as with the others. However, interestingly, this tone has affected the outer surface quite a lot. In fact, I can say that the angled part is more matte, while the rest of the areas are shinier. So here we have the opposite situation. This has resulted in a more mottled appearance on generally flat surfaces. The layers are nice, the surface quality is good, but as I said, there is a constant transition between glossy and matte. When I look at the flat surface, overall I can't say there's a major problem. There are very small rough spots in a few places. If we move on to the scoring, Hyper continues in a very consistent manner. I give it 4 points. CR gets 3 points right behind it. While Ender Fast PLA gets 2 points, since the appearance of the outer surface is more important to me, I give Ender PLA 1 point. Yes, you are seeing one of the standard test models I use. This is the Dragon model. I have used this as a test print in many review videos as well. Since it's a model printed without supports, there are naturally some droops on it. There are also droops on this very expensive filament. In fact, I can say that in some spots they're a bit excessive. I also notice slight vibration effects again. If this happens on this model, usually there are small stringings at the very top part. However, there is no stringing on the print. Again, because it has a lot of indentations and protrusions, some vibration effects are also visible on the model. When I move on to the print I made with the expensive filament, the first thing that catches my attention is that it's extremely shiny, and unlike the previous prints, there is no situation where some areas are matte and others are glossy. The distribution of gloss on the model is quite homogeneous. When I look at the overhanging parts on the model, they are located at the same spots as in the previous model. However, this is much less pronounced and the vibration effects are not as noticeable as with the very expensive filament. It's a very successful print. When I move on to the mid-range filament, I also see a glossy surface. There is no matte effect at any point. Just like in the other models, similar drooping has occurred at similar points. I can say that the amount of drooping here is closer to the print I got with the very expensive filament. You can see the print I made with the budget filament. Just as it caught my attention, it will surely catch yours as well. The transition from matte to glossy and from glossy to matte that we saw in the other prints continues on this model as well. While the other filaments achieved consistency on this model, the cheap filament once again resulted in a poor outcome here. There is excessive drooping. The vibration effects are much more pronounced in the indented and protruding areas, and once again, the print quality is not at a level that would satisfy me. When it comes to scoring, in my opinion, the expensive filament was especially very good in terms of surface quality. That's why I give 4 points to the expensive filament. Again, due to its successful surface quality and the complete absence of vibration effects, my 3 points go to the filament in the mid-price segment. Right behind it with a small difference comes the very expensive filament, earning 2 points. And as for the cheap filament, honestly, after the other prints, it didn't surprise me in this print either. It had poor surface quality and gets 1 point. Now let's quickly look at the same prints on the Creality side. Hyper PLA, I don't see any color tone difference in the print. There are also no noticeable vibration effects that could be considered serious. There is no stringing at the top sections. As with all the other prints, there is sagging, but I can say it's a bit more than I expected. The print I got with Creality CR PLA might be a bit more matte compared to Hyper, but the surface quality is at least as good. There is no noticeable vibration effect. There's no stringing in this one either. In fact, compared to Hyper, I can say that it produced a bit less sagging at steep angles. You are seeing the print I made with Enderfast PLA. Overall, its glossiness is nice, but where there are steep angles, again, I think there is a difference that might only be noticeable to the eye. I'll try to show this to you in the photos, but it may not be very obvious. There is a subtle difference in tone as well. The parts with steep angles look a bit shinier compared to the other sides. There was no stringing on this model either, and although the sagging at steep angles is at an acceptable level, when ranking it can be said that it is among the models with more sagging. I'm looking at the print I made with Creality Ender PLA. Here, the transition between matte and glossy parts is more pronounced. I will probably be able to show this to you very clearly as well. There is nothing wrong with the overall surface quality. As with the others, sagging is of course present on it. There is also no significant vibration effect or stringing on the model. If you ask me, as a result of these findings, CR PLA is ahead of Hyper and deserves 4 points. Right after that, with a slight difference, comes Hyper PLA. At Enderfast, there were slight differences in surface gloss. Therefore, I give 2 points to Enderfast PLA, and since this difference is more visible, I give just 1 point to Ender PLA. At this point, we're taking a short break in the video for a brief announcement. Actually, I'm not speaking English right now. In fact, I don't even know English, but thanks to Hagen AI, a powerful artificial intelligence tool, I can deliver my video content to you in English. In fact, if I wanted to, I could even start speaking Spanish right now.
Quizá debería abrir un nuevo canal de YouTube para mis publicaciones en español.
Or maybe in Japanese.
日本人ってテクノロジーの面ですごく進んでるんじゃないの？もしかしたら新しい YouTube チャンネルも日本語でやるのもありかもね。
If you also want to publish your content globally like I do, you can use Hagen AI, which provides dubbing support in more than 175 languages. Let's pick up where we left off. Now we're moving on to this alien bust, which is another standard test model for me. Usually it's a print I do one after another to test whether printers produce consistent results. The reason I prefer this model is that it has both indentations and protrusions, and since it requires supports in many areas, I can observe any sagging or color changes that may occur. First of all, I should say that I had no trouble at all removing the supports. So of course, the settings I used played a big role here, but there was no difference from filament to filament either. I was able to easily remove the supports from all the prints. Right now, you're looking at the print I made with a very expensive filament. I'm quite satisfied with the surface quality. I don't notice any problems. The sagging in the areas where I removed the supports is completely normal. There's no problem here either, only on the back of the head. As with some other prints, there's a transition from a glossy surface to a matte one. Again, of course, this area corresponds to where the print slows down and makes an outward protrusion at a right angle. Other than that, it's a successful print. When I look at the expensive filament, the number of transitions from glossy to matte surfaces is much higher. As you can see, these can vary greatly from model to model. While there was no color change on the Dragon model just now, you can get different results when you print a different model with the same settings. This is a great example of that. There is no sagging at the support contact points. It has delivered a successful result here, but as I said, there are too many transitions between glossy and matte on the overall surface. And when I look at the filament in the mid-price segment, the glossiness is almost exactly the same everywhere. Only, as with the expensive filament, there is a slight increase in glossiness at the back of the head, but the difference is not as obvious as in the others. The overall surface quality is also quite nice. You can see the print I got with the budget filament. Again, at first these matte areas can be a bit misleading. Since the layer lines are not very pronounced, it gives the impression of having a very nice surface. However, when you examine it closely, you can see that it still causes flow problems, creates roughness on the surface, and the protruding points where the print slows down are much shinier compared to the general surface. As for the support contact points, there is no difference from the other prints. It's at a very minimal level, but again, I didn't like the surface quality of this print. When I evaluate these results, in my opinion, the most successful print came from the filament in the mid-price segment. That's why my score is 4. The very expensive filament produced a result close to this. My score is 3. There is some inconsistency with the expensive filament. It may not deliver the same performance with every model. I also didn't find the surface quality here very successful. My score is 2. The cheap filament continues its consistency. As you can see, the surface quality was poor. My score is 1. Let's see how the results will be on the Creality side. On the model printed with Hyper PLA, there aren't such sharp transitions between glossy and matte surfaces. The surface quality is quite successful. There is also no sagging at the support points, just like in the previous models. There are natural and reasonable levels of roughness. When we look at the area where the difference is usually most apparent, I can say that there is a difference in glossiness between the two surfaces, but it's not very obvious. We continue with CRPLA. The surface quality is extremely successful. There is no vibration effect. There has been no change in the surface gloss. The roughness where the supports were removed is at a reasonable level. The difference in glossiness that appears on the back of the head is quite minimal. Honestly, when I put it side by side with the Hyper, I would have a hard time determining which one gives better results, because they look almost like copies of each other. You can see the print I got with Enderfast. There is a consistency in these filaments. What I said is very similar to what I observed with the Dragon model. Just like I said for the Enderfast Dragon model, there are subtle spots where the shine changes. The same thing applies to this Alien model as well. The surface quality is good, I have no complaints about that. I also don't observe any extra sagging or roughness where I removed the supports. At the back of the head, there's again a difference in shininess. I'll say the same thing for Ender PLA as well. The differences in shininess that started at Enderfest have increased even more with Ender PLA. The changes on the surface are much sharper. Again, where I removed the supports, there is no sagging or extra roughness. The difference between the shiny and matte parts at the back of the head is also extremely clear. Honestly, I went back and forth a lot between CR and Hyper PLA. I examined details that I can't even show in the photos, and even though they are very similar, I decided that if any filament is going to get 4 points, it should be CR. Right after that comes Hyper PLA. 3 points. Enderfast gets 2 points due to minor changes in gloss, and Ender PLA gets 1 point because of a more pronounced change in gloss. After examining the surface qualities a bit, we will now slowly start looking at the technical details. What you see is actually a combination of many different test prints merged onto the same model. In my opinion, one of the most important aspects of PLA filament is related to stringing. Stringing is also highly related to the printer itself. However, even if you put a low-quality filament into the world's best printer, it can still cause stringing. The same goes for tests like sagging. As you can see in the print I made with the very expensive filament, there isn't the slightest bit of stringing. Here, neither the printer nor the filament caused me any problems. Just below this stringing section, the printer creates opposing bridges without using any supports. I should mention that in the bridge section, the amount of sagging is not at a very low level. In the right-angled sections just below, there are some structural deformations at certain points, though not everywhere. Again, I'm looking at the unsupported right-angled section. There is no significant deformation on the top surface. Maybe when it reaches the part labeled 15, there's a slight deformation on the top surface. But when we look at it from below, I observe that sagging starts to increase, especially after 20 degrees. Right next to it, you see a bridge test. Here as well, a bit of sagging can be observed on the longest and the one just below the longest section. Now we're moving on to the expensive filament. The result is again quite successful in the stringing section. However, there is excessive sagging on the underside. In fact, in the sections with a steep angle, structural deformations have also increased compared to the very expensive filament. The result in the angle test, however, is not bad at all. Here, the sagging is at a level that can compete with the very expensive filament. I don't see any serious problems on either the bottom or the top surface. When we look at the bridge test, there is almost no sagging here either. This is the print I got with the filament in the mid-price segment. Again, there is no stringing. I'm going through these parts quickly now because in fact we won't see this in any of them. The sagging in the bridges formed just below is at a very low level. It's there, but among all we've evaluated so far, the least amount belongs to the mid-range filament. Again, when we look at the shapes at right angles, we can see that there is no structural deformation and the print is extremely neat. When we look at the angle test, the top part is quite smooth, while on the bottom part, yes, a difference becomes noticeable after 20 degrees. But the sagging is almost negligible. When I look at the bridge test, perhaps only the longest one at the very top shows a slight sagging, but there are no problems with the other shorter bridges below it. We're looking at the cheap filament. There is no stringing with the cheap filament either. On the bridge below, the sagging is quite significant, and just below that, the right-angled sections also show considerable structural deformation. I'm looking at the right angle. There are slight roughness and color changes on the top surface. On the bottom side, however, I can't say there's any significant sagging. There's also no significant sagging in the bridge section. Taking this data into account, especially due to its performance at right angles, I give 4 points to the filament in the mid-price segment. Right after that comes the expensive filament, 3 points. Very similar results were obtained. The very expensive filament received 2 points. The cheap filament, which had more sagging and structural deformations compared to the others, received 1 point. Now let's look at the Creality Hyper. There is no stringing in this filament either. There is sagging as there is in all of them. But I think what we see here is again one of the best results. It's at a slightly lower level compared to the others. It can be said that the result is close to the mid-range filament on the other side. There is no structural deformation in the vertical angled sections underneath. A nice print has come out at a precise angle. I'm looking at the angle test. There is no problem on the top surface. When I look at the bottom side, it can also be said that it gave one of the best results among the tests. It can't even be called sagging. There is just a very, very slight roughness. I'll say the same thing for the bridge test. So only on the top two, I notice a very slight sagging. Other than that, the results are quite successful. We're looking at the print made with CR filament. There is no stringing in this model either. The sagging on the bottom side is also minimal, just like with the Hyper. There is no structural deformation in the areas with sharp angles. These parts also turned out well. I'm looking at the angle test. It could even be said that the top surface is the best among all the ones we've seen so far. The result on the bottom side is also very close to the Hyper. Let me show them side by side like this. These two filaments really deliver results that are very close to each other. Even though they're very similar, if I had to rate one, I would say Hyper is just slightly ahead when it comes to sagging. Again, in the bridge test, we see a similar result. There is almost no sagging except for the two longest bridges at the top. Now we've come to the Enderfast PLA. There's no stringing. Sagging has increased in the section just below. You could even say it's a bit too much. In the right-angled areas below that, structural deformations have occurred. There are serious rough patches here. There are no problems on the upper part of the angle test. When I look at the lower part, there is a very slight amount of sagging. These are very small differences, of course, but looking at the bridge test as well, I can say that compared to the previous filaments, especially the Hyper and CR filaments, the sagging is a bit more pronounced. We're now on the Creality Ender filament and there is no stringing. The sagging is almost as minimal as it is with the Hyper and CR filaments. On the vertical angled sections underneath, it has produced results that are nearly perfect, but I did notice some slight structural deformation at the very bottom parts. There is no problem on the upper part of the angle test. It came out quite smooth. When I look at the bottom part, the sagging is actually at a reasonable level, just like in the other tests. Honestly, I haven't come across any filament here that sags significantly. The bridge test can also be said to be similar at Ender Fast. There's a bit of sagging at the very top part. As you go down, this decreases gradually. When I evaluate these results, I think the most successful test model was the one made with Creality Hyper PLA. Right after that comes Creality CR PLA. At this point, I can say that Ender Fast disappointed me a little, because there was a lot of deformation in the steep angled lower sections. That's why I'm giving 1 point to Ender Fast and 2 points to Ender. By the way, let me mention this. Creality Hyper PLA is considered mid-range among the filaments in the other segment. I just said this for informational purposes, so you don't categorize it as a very expensive filament. Yes, the tests aren't over yet. We've looked at the surface quality, we've briefly touched on various technical features, but in my opinion, some mechanical properties of PLA are also important. For example, the material's tensile strength, elongation rate, or impact resistance. Frankly, these are also important details. To test this, I printed the parts you see here, which are called dog bones. These have dimensions specified in ASTM or ISO standards. Both are international standard systems. However, ASTM is more widely accepted in America, while ISO is recognized in Europe. Recently, especially in 3D printing tests, ASTM has started to become more valid. I will share the test results with you in a moment, but first I want to point this out. These tests were not conducted in a laboratory environment in a certified manner, and we are people with a DIY mindset, so our tests had to be in line with that. My dear brother Erbil Yuruk recently shared a very useful piece of content on his own YouTube channel, Let's Make Something. He tested PLA, PETG, and ABS from many different perspectives and compared them with each other. If you haven't watched it yet, I suggest you check out that video right after this one. I've put a tag above and left the link in the description section. This video also included tensile and braking tests. He got great results with a machine he designed and built himself. When I told him about my project, he said he could help me with this, and he played a major role in sharing these results with you. That's why I want to thank Erbil again here. As for the results, you can see various lines in the middle section. This shows how multiple samples were tested, the force applied, and on the downward graph after the breaking point where the material yielded and where it broke. Their mathematical equivalents are written right on the right side. I won't go over each of these one by one, because in my opinion there are two important points. One of them is already the direct result of the tensile break test. That is the megapascal value written at the very bottom. As you can see, the very expensive filament reached a value of 48.13 megapascals, and after this force was applied, the break occurred. Before breaking, it stretched by 1.48 millimeters. The megapascal value here shows the tensile strength of the material. Of course, this is based on the test piece we made. As the name suggests, elongation refers to how much it stretches before breaking. A high elongation value does not necessarily mean that the material will be flexible. But it does give us important insights about this. Apart from that, filaments with higher elongation values generally have higher impact resistance compared to those with lower values. You can keep these points in mind when looking at the values I'll show next. Now you are seeing the test result for the expensive filament. Its tensile strength turned out to be a bit better than the very expensive one, 53.12 megapascals. The elongation value of the filament before breaking is 1.26 millimeters. When we move on to the mid-priced filament, we see the megapascal value as 50.91. The filament stretched 1.17 millimeters before breaking. What you're seeing now are the test results for the cheap filament. The tensile strength of this filament turned out to be 45.91 megapascals. The elongation value of the filament is 1.21 millimeters. Let's also examine the results of the same test on the Creality side. Creality Hyper PLA reached a pretty decent value of 56.23 megapascals, and during this test the material stretched by 1.4 millimeters. The tensile strength of Creality CR PLA is 50.85 megapascals, while its elongation value is 1.12 millimeters. When we move on to Enderfast PLA, the tensile strength is 49.73 megapascals, and the elongation value is 1.24 millimeters. And finally, in the test conducted with Ender PLA, the tensile value is 53.18 megapascals. The elongation value during the test was measured as 1.24 millimeters. Now, I want to show you all of these together in a single graph. As you can see from the tests, the highest value, 56.2 megapascals, is with hyper PLA. Then, perhaps unexpectedly, Ender PLA comes next. Third place goes to the expensive Filament. After that is the mid-priced Filament, and just below that is Creality CR PLA. When we get to the last three, we see the ranking of the Enderfast, the very expensive and the cheap filaments. The term megapascal might be new for some users, and you may not fully realize what it actually means. That's perfectly natural. After all, we just did a small tensile test on a part. Okay, we saw a graph, but what does it really mean? For example, how many kilograms can this pull? There isn't a direct kilogram equivalent for megapascal, so we can only determine this using a formula, because it varies greatly depending on the diameter, thickness, and infill rate of the printed part. In other words, we can't say that this many megapascals equals that many kilograms. However, if we use a formula, I can show you how many kilograms that dog bone I just showed actually withstood according to the results. What you're seeing now shows us the approximate tensile strength of the test models after the formula calculation has been done. Hyper PLA was already in first place with 56.2 megapascals. Its approximate tensile strength corresponds to 103 kilograms. As you can see, it continued to decrease. We didn't change the previous ranking at all. The cheapest PLA, on the other hand, yielded a result of 45.9 megapascals. Its approximate tensile strength was 84.2 kilograms. I don't want to base the scoring here solely on the megapascal value, because it's also necessary to consider the consistency of the diameters for each sample you see and their prices. Taking these into account, in my opinion, the mid-range filament deserves 4 points. Then I give 3 points to the expensive filament that delivered the strongest result, 2 points to the cheap filament that always failed in print quality but managed to finish the tensile test without embarrassment, and 1 point to the very expensive filament that still ended up at the bottom of the ranking. On the other hand, whether you look at it in terms of megapascal value, elongation value, or price, it's very clear which one deserves 4 points. Hyper PLA. Next comes the surprise of the day. It lagged behind other Creality brands in print quality, but both its mechanical properties and the deviation rate in the tests are very low. That's why Ender PLA gets 3 points. Right after that, CR PLA gets 2 points, while 1 point goes to Enderfast. After all these results, our overall ranking is as follows. The filament in the mid-price segment became the one with the highest score, collecting 24 points. Next, the very expensive filament received 20 points. The total score of the expensive filament is 18, while the budget filament remained at 8 points. Looking at the Creality side, Hyper PLA collected most of the points and took first place with 26 points. Next, the CR filament, which received 22 points, took second place, while Enderfast and Ender PLA shared third place with 11 points each. I've shared the overall scores with you, but there was one more test I conducted. This is actually one of the main reasons why clogging problems occur most frequently: the diameter and ovality of the filament. So, what did I do for this? I measured the diameter of each filament at 10 different points. I left at least a few meters of space between the points where I took measurements, and then I measured each of these sections from 2 different angles to try to create an ovality map. Of course, in industrial production, these measurements are done with laser machines. Results obtained with precise measuring tools like digital calipers or micrometers cannot provide definitive results. However, I was as careful as possible. While measuring the filaments, I neither held my hand too loosely nor squeezed too hard to crush the filament. In my test, the average diameter of the very expensive filament was 1.744 millimeters. This is very close to the optimal value of 1.75. The ovality was not bad at all either. Its average was 1.746 millimeters, and during the 30 measurements I made for ovality, the maximum diameter difference was only 0.03 millimeters. The expensive filament, although just slightly, fell a bit below the standards. Here, the value dropped below 1.70, and I obtained a result of about 1.697 millimeters for the diameter. The same value was also valid for ovality. The result is 1.693 millimeters. In fact, there was diameter consistency because the ovality differences did not exceed 0.03 millimeters. But due to a production-related issue, I think the diameter value even fell below 0.70 millimeters. When we look at the filament in the mid-price segment, the average value of measurements taken from 10 different spots was 1.735 millimeters. It also has the distinction of being the only filament whose ovality matches its diameter. The average ovality was also 1.735 millimeters, and the maximum difference between measurements taken from the same spot was 0.02 millimeters. For the cheap filament, the average diameter measured from 10 points was 1.725 millimeters, while the average ovality was 1.731 millimeters. The filament with the most measurement inconsistency in ovality measurements was the budget filament. Here the difference rose up to 0.06 millimeters. When we look at Creality Hyper PLA, the average of the measurements taken from 10 different points was 1.744 millimeters, while the average ovality was 1.737 millimeters, and the difference between the ovality measurements did not exceed 0.03 millimeters. Creality CR PLA had an average diameter of 1.721 millimeters, while the average ovality was 1.723 millimeters. The largest difference between the ovality measurements was only 0.02 millimeters. The Enderfast's average diameter, which was the closest to 1.75, was 1.749 millimeters. Its ovality was 1.742 millimeters, and in the ovality calculation, the difference did not exceed 0.03 millimeters. When we moved on to Ender PLA, the average diameter was 1.741 millimeters, while its ovality was 1.737 millimeters, and again, the ovality difference did not exceed 0.03 millimeters. I won't be giving a score regarding the diameter consistency of the filaments because most of them were quite successful. Both the diameter and ovality consistency of the filaments turned out to be very good. The only one I wasn't satisfied with here was the expensive filament. Why? It stayed below 1.70. In other words, we needed to be between 70 and a maximum of 80, so even if it was on the borderline, in my opinion, it doesn't deserve a point. The budget filament was within the limits. However, in the ranking, the diameter inconsistency was very high. I mean, sometimes I measure 1.70, sometimes 1.69, sometimes 1.77. There were significant changes in diameter. The same goes for ovality. Even though it seems to stay within the limits, when you take the average, there was so much inconsistency that, this happened in just 1 kilogram of filament. If I were to use 10 kilograms, it looks like after a few spools, it could cause a clogging problem or an underfeeding issue. I didn't like these two filaments. I didn't like either the cheap filament or the expensive filament. As for the others, I give all of them full marks, because both their diameter standards and ovality consistency were quite good. I think these tests are valuable, but they don't and can't prove anything definitively, because they need to be subjected to much longer tests. Maybe at different times with different production dates, you might need to buy a few kilos of these filaments and test dozens of kilos at the same time. Even that alone wouldn't be enough. Why? First of all, there's the printer factor and the factor of the settings here. Even if nothing else, there's the environmental factor. It may not prove anything, but it definitely gives you an idea. Here's what I've come to realize. You can't generalize that expensive filament is good in every aspect. While the surface quality may look nice, it might have excessive sagging at steep angles, or its mechanical properties may not meet your requirements. A cheap or mid-range filament may actually provide you with more than what expensive filaments can offer. In my opinion, Hyper PLA was the best in these tests. In fact, I always mentioned it among the top choices when people asked me, but this was the first time I actually put the filament through a test. It didn't disappoint me either. Since it is also in the mid-range price segment, I think it's a true price-performance product. So hobby users can also choose this, people who care about print quality can also prefer it, or due to its mechanical properties, professionals who want to use a PLA in their field can also opt for Hyper PLA. I would put the mid-range filament in second place. The print quality was quite good. I think it reinforced this with some of its mechanical properties as well. It can be used in any project where PLA is needed. I also liked the Creality CR. In most prints, it performed head-to-head with the Hyper. Its results in the Tensile test were also within normal values. Would it be used? Yes, it can be used in any area where PLA is preferred. It won't disappoint anyone, but the price is very close to the Hyper. For that reason, if it were me, I'd pay a little more and get the Hyper PLA. Overall, I like the filament, even though it's very expensive. Although it caused slight sagging at steep angles, the prints were generally good. There was almost no difference in tone and gloss. Still, is it worth the price? Instead of buying this, I can get 2 filaments from the mid-price segment and still have money left over. So in my opinion, it didn't really deliver what its price promises. Next up are Enderfast and Ender PLA. I think the print quality was below that of the Hyper and CR. I can't say it's bad, but I'm still more inclined to spend a bit more and buy filaments from the mid-range segment. But if you say even a little, I don't want to spend any more money on top of this. If your work is a hobby, or if you're going to make and sell gifts or decorative items, yes, you can use it in such areas. Cost might be important for you. Therefore, in such cases, Creality Ender or Enderfest PLA can be preferred. The expensive filament, especially in terms of print quality, failed when you consider its price. Its tensile strength was high, but it still lagged behind some more affordable filaments. The cheap filament, on the other hand, was inadequate in many prints. I didn't like the surface quality. There was a flaw or a problem in every print. I didn't find it sufficient even for hobby use. You can't achieve high speeds, and the likelihood of problems is high. Even considering the cost, I wouldn't buy this cheap filament. By the way, I also saw this very clearly myself. I mean, those who follow the channel probably already know this. I'm someone who makes a lot of review videos. Now, if I review this printer using a budget filament, I'll be telling you different things. And if I use an expensive filament, or one that's above a certain quality, and review the prints, I'll be telling you something else. Actually, I already pay attention to this. I mean, I always use filaments that are above a certain level, above a certain quality. I try to do reviews with brand new filaments as much as possible, but as you can see, a lot of things can change. That's why I think this turned out to be a good idea even for those who want to see the maximum performance of their own printer. Now let's get to your test results. If you still haven't left a comment and joined the test at the beginning, these are your last seconds. Which of the prints in this image was the cheap one and which was the expensive one? For those who participated in the test, I'm announcing the results. Yes, the print in option A belonged to the filament in the mid-price segment. Option B was the expensive one, option C was the one printed with the very expensive filament, and option D was the budget filament. As I said, we can continue discussing together in the comments which one looked good and which one didn't. I also want to congratulate those who could identify the filament quality just from a single photo. Yes, that's all I have to say on this topic. I hope this video has been very helpful for you and that I was able to give you some ideas. I'm looking forward to your comments about the video and any questions you may have. I would be happy to answer all of them. May your printer run smoothly and your prints be flawless. See you in the next video. Take care.